Now we will talk about what happens to a particle when a charged particle when it moves in an electric field. Now when the charged particle enters a field generated by other source charge or charges, then evidently it will experience a force because it has a charge. Now if that is the only force acting on that particle, then in this case it will be a net force, and so the particle in this case will accelerate, and according to Newton's second law, under this net force. Now this is what we will be talking about now. Quantitatively, this is the situation that arises. The net force or the electric force on the particle, which is the net force if it is the only force, is just equal to Q, the charge of the particle, multiplied by the electric field. And this net force is equal, according to Newton's second law, to the mass multiplied by the acceleration vector. This is a vector equation, and remember that what we have said, that in this equation, when you substitute them in the vector form, you substitute Q here along with its sign. Okay, so this is the relation between the charge of the moving particle, the electric field, which is that as a result this is the net electric force, and the acceleration of the particle. Now, if the field is uniform, then the acceleration is constant. Now, this relation is true for any field, but in the case when the field is uniform, since the charge is constant and this whole force is constant, and since the mass of the particle is constant, then the acceleration in this case, which is just equal QE over m, is also a constant. And so we will have a situation where we have a particle that is moving under constant acceleration. Now we have learned in the mechanics part of this course how to study the kinematics of such a particle by using the equations for the model of a point particle with constant acceleration. And we can apply now these equations to this particle. Now it's important to note here that from this equation it's clear that if the charge is positive, then since mass is positive, then the acceleration is parallel to E, because when a positive number multiplied by E, you will get a vector along E, and since m is positive, then in this case A will be along E. However, if the charge is negative, then in this case the acceleration will be opposite to the direction of the electric field. Okay, this is will be clear when we consider this example. Here we have a uniform electric field, and this uniform electric field is directed from down upwards, as you can see here, and we have an electron which is a negative charge, and this electron enters the electric field at some point here with a given speed, which is horizontal speed along the positive y directions. Now the electron will undergo a downward acceleration. Why? Because its charge is negative, and so the direction of the force is opposite to the field, and so the direction of the acceleration, which is along the same direction of the force, is also opposite to the field. So the force on the electron as it enters the field will be downward. And because the field is uniform, then that force will be constant, and the electron will undergo a constant force downwards, which means it will move with a constant acceleration downwards. Now, so the acceleration of the electron will be always downwards. But this doesn't mean, as usual, we know that the direction of the force and the acceleration and the direction of the motion do not need to be the same if the particle has an initial velocity. And so this is as is the case here. So we have here the electron entering here with a given velocity. It will accelerate downwards, and it will move like a parabola. This is exactly like what you have when you project an object horizontally in the gravitational field of the Earth near the surface, where you will have this parabolic trajectory, and this is how it will move. Now, another example is we have a positive charge that is released in a uniform electric field. Now, we will do this in more details on the board, but the example is the following. You have a uniform electric field again, which is directed from left to right, so it is directed along the positive x direction, and it is generated in the space between two oppositely charged planes, and the distance between the planes is d. Now, an electron, or sorry, a positive charge is released near, just near the positive plate, and it has with an initial speed equal to 0. Now, the question is, we want to find what is the speed of this particle when it almost touches the second plate, or the negative plate. Okay, that is after it travels a distance d. And we are requested to do this using two methods. The first method is the speed using kinematics, and the second is using energy conservation or energy methods by treating the charged particle as a non-isolated system. Okay, so let's see how we can do this.